Let us discuss evaluating piecewise function. But the first thing we need to understand is the definition of piecewise function. So we consider x minus 1. Let's say this is x and this is 2. Okay, what if these three functions are combined or placed in a single function? So they are all together and you have to name it as a single function. Let's say that is function g. So we have g of x is equal to these 3. Okay, now these 3 are considered to be the sub-functions, meaning to say these are parts of a single function g. Now, because we are referring to function, we must define the necessary subdomains of this function g, meaning to say the subfunctions x minus 1, x, and 2 must have distinct values of x, meaning to say if I say that the domain of g of x that is equal to x minus 1 is a set of all real numbers x which are greater than 1. So if you set that as a domain of g of x is equal to x minus 1, then make sure that the domain of g of x equals x must be distinct. So we may say x is equal to 1. So the other g of x is equal to 2 must also have its distinct domain. So you may say x is less than 1. And as you try to observe, these subdomains are distinct. So if you try to place it in a real number line, and let's say this is 1. So x that is greater than 1, meaning to say unshaded, then it goes to right. So you may say that is, okay, in interval notation, greater than 1, then it goes to positive infinity. While the other x is equal to 1, so meaning to say it is shaded here. That is x that is equal to 1. It must be shaded to indicate that that is a single point. Okay, now the other x is less than 1 would also mean that you are just referring to the set of all real numbers less than 1. So that is x that is less than 1 or negative infinity in interval notation. Okay, now this is how we define piecewise function. We have what we call the necessary subfunctions. So we have x minus 1, x, and 2, and those are just part of a single function g. And each subfunction must have its own domain. So as you observe, we have x minus 1, x is equal to 1, x is less than 1. So these are the conditions, meaning to say it varies. Therefore, it will only give you the clue what must be used when you first have to indicate also the value of x. So piecewise function is like a collection of two or more functions combined together. So you are defining their subfunctions and it is a single function already. So piecewise function seems like a mother function to two or more subfunctions, be it trigonometric functions, logarithmic functions, exponential functions, or any other functions combined together. Okay, so that is a piecewise function. These subfunctions will help us identify the value of each y. Okay, and we also use the subdomain for us to know what subfunction are we going to use. Let's say, for example, when the given x is, let's say, 2. So we need to understand that 2 is greater than 1. Therefore, its corresponding function that must be used when x is equal to 2 must be g of x is equal to x minus 1. However, if you have x that is equal to 1, so it is understood that you are using g of x is equal to x because 1 is part of the interval, or simply x that is equal to 1. However, when x is, let's say, negative 10, and we know that negative 10 is less than 1, so meaning you are going to use the subfunction g of x is equal to 2. So meaning to say, if you're trying to evaluate, let's say for example, what is the value of g of 0? So 0 is less than 1. Okay, so you're using g of x that is equal to 2. So g of 0 is simply 2. Also, if you're looking for the value of g of, let's say g of 5, and 5 is greater than 1, so you're using g of x is equal to x minus 1. So you substitute g of 5, let x be equal to 5, so 5 minus 1 is 4. So that is already the implication of the subfunctions and the domain in evaluating piecewise functions. Let's have more examples. So let us consider this. F of x is equal to x squared, 3x, but as you observe here, you can only use x squared, or f of x is equal to x squared if x is less than or equal to 1. However, you can use f of x that is equal to 3 when the value of x is greater than 1 but less than or equal to 2. However, you can have f of x that is equal to x when x is greater than 2. So it means to say you have to identify first the value of x and where can you place this value of x. So you are trying to satisfy the conditions set. Now these are the if conditions. Okay, so when we are evaluating, let's say we are trying to know the value of f of 0. So the first thing you need to do is to identify where can you find 0. So can we consider it or found it in the interval x that is less than or equal to 1? Okay, so obviously in green function here, we can use f of x that is equal to x squared as a function for us to know f of 0 because 0 is less than 1. So it is part of this condition set by the first subfunction. Therefore, f of 0 now is equal to the square of 0. So f of 0 is 0. Okay, so let's have the next. Let's say you're looking for the value of f of 5. So the x input value is 5. So you can observe x that is greater than 2 subfunction. So we can use f of x that is equal to x because 5 is greater than 2. So pasok siya sa condition nito. Okay, so we use f of x that is equal to x. So we let x be equal to 5. So f of 5 is 5. Next, so what about if you're looking for f of, let's say, 0.3. So f of 0.3, and we know that 0.3 is less than 1. Okay, and we can now use f of x that is equal to x squared. We substitute, so we have f of 0.3 is equal to the square of 0.3. So getting the square of 0.3 will give us 0.09. Let's have the next. So what if we're looking for f of 1.5? Okay, 1.5 is found between 1 and 2. So we are going to use f of x is equal to 3, a constant function. So we're looking now for f of 1.5, and because that is a constant function, the resulting value will always be 3. So the answer is 3. So next, let's say we're looking for f of 10,000. And 10,000 is obviously greater than 2. So meaning to say, we can use f of x that is equal to x. So f of 10,000 is itself 10,000. That is an identity function. So this is the graph of function f, and as we notice, it is broken into pieces. The reason is because function f is simply a piecewise, so it's like broken into pieces. And as we observe, there is a curve here that is actually a parabola. That is the resulting graph of f of x that is equal to x squared for all values of x which are less than or equal to 1. And as you observe, the graph is cut when x is already 1 here. Okay, but as you move from 1 to 2, so 1 is excluded, and another subfunction f of x is equal to 3 is already included because the values of x is already restricted less than or equal to 2 but greater than 1. So you're now using f of x that is equal to 3, a horizontal line. However, when the values of x are greater than 2, then you are now using the identity function f of x is equal to x for all values of x greater than 2. And the graph is specific. This one is excluded, annotation for exclusion, because 2 is not part of f of x that is equal to x based on the set condition. Okay, so normally when we talk about piecewise functions, then the graphs vary. The next given talks about constant functions. H of x is equal to 1 if x is greater than 2. So you see the condition here. You can only use h of x that is equal to 1 if the value of x given is greater than 2. However, you use h of x that is equal to negative 2 if x is less than 2. Let's try to answer. So what is h of 2? So the value of x here is 2. Can we find 2 from any of these two conditions set by the domain? So obviously we cannot find it. Therefore, h of 2 is simply undefined. It is already undefined because no part or no subfunction has 2 as an element of its domain. Okay? So what about h of 10? And 10 is obviously greater than 2, so we can use h of x that is equal to 1. So h of 10 is simply 1 because that is a constant function. What about h of negative 62? Negative 62 is less than 1. Okay, so we're using h of x is equal to negative 2. And that is still a constant, so h of negative 62 is negative 2. We can also have operations just like this. H of 6, add that to h of 1. Okay, so in this case, we need to be specific on the value of x. X here is 6. Then we try to know where can we find 6 on the given interval. So it is found on the first subfunction, h of x is equal to 1. So meaning to say, h of 6 is 1. What about h of 1? And 1 is obviously less than 2. So that is equal to negative 2 because the function that is required already is h of x is equal to negative 2. So negative 1 plus negative 2 1 plus negative 2 is negative 1. So how does the graph look like? H of x is equal to 1. Let's say this is 1. This is 1. Okay. So the other is h of x is equal to negative 2. Let's say this is negative 2. If we look into the domain, if x is greater than 2, then h of x is equal to 1. Let's say this is 1, so this must be 2. So when when x is 2, h is 1, but that is excluded, right? So we exclude it, then this moves to positive infinity. So this is for h of x that is equal to 1, and that is true for all values of x greater than 2. However, h of x is equal to negative 2 when x is less than 2. So meaning to say, it is not part, 2 is not part of the values, so it moves here. Okay, so this one is for h of x that is equal to negative 2 for all values of x less than 2. So that is the illustration of the graph of h of x. The next example, m of x is equal to x if x is greater than 1, and m of x is equal to 5 if x is less than 1. Okay, so let's try to evaluate. Let's say, for example, what is m of 10? 10 is obviously greater than 1. So meaning to say, we are using m of x is equal to x, because that is a subfunction that contains all values of x greater than 1. So m of 10 is itself 10, identity function. Let's have m of negative 5. Negative 5 is less than 1. Okay, so we're using m of x is equal to 5. That is the required function. So m of negative 5 is 5. That is a constant function. Okay, and still we can combine. Let's say, for example, let's have the division. So what is the quotient of m of 2 when that is divided by m of negative 2? So you see, 2 is greater than 1. So m of 2, since 2 is greater than 1, then we're using m of x is equal to x. So m of 2 is 2, identity function. So this must be 2. For negative 2, and that is obviously less than 1, and its required function is m of x is equal to 5. So that is a constant function. So m of 2 is simply 5. So our answer for m of 2 divided by m of negative 2 is 2 over 5. So we can also have m of negative 2 plus m of 5 minus m of, let's say, negative 10. Okay, so when we're solving this kind of operation, just be cautious enough on the values of x and you try to locate where does this value of x. Okay, so when x is negative 2, it is obviously part of the second subfunction m of x is equal to 5 because negative 2 is less than 1. So that is simply 5 because of constant function m of x is equal to 5. But for m of 5, because 5 is greater than 1, okay, so m of 5 is equal to 5 because we are using m of x is equal to x simply because 5 is greater than 1. So here the answer is 5 minus, so we see here negative 10, and negative 10 is less than 1 So we are using m of x is equal to 5. So we have the answer that is 5, because that is simply a constant. M of negative 10 is 5. So we have minus 5. So 5 plus 5 is 10, minus 5 is 5. The answer is 5. Okay, so how does the graph looks like? Say for example, this is 1, 2, 3, 4, 5. So this is 5. Okay, let's just have to label it. So when x is less than 1, then all values of x which is less than 1 will fall under the subfunction m of x is equal to 5. So if this is 1 and 1 is excluded, then it forms a horizontal line. Okay, so that is for m of x that is equal to 5 for all values of x less than 1. However, when x is greater than 1, then we have m of x is equal to x. So x, then we have m of x. So let's try to tabulate it. If x is 1, then m of x, supposedly that is 1 also. However, that is excluded because of greater than signs. Okay, but we just need to know for us to locate where can we possibly have the starting position. So m of 1 is 1. So m of 2 is 2. Identity function. Okay, so naggagayahan sila. M of 3 is also 3. So if this is 3, okay, so this is how identity function m of x is equal to x looks like. Okay, so we have m of x is equal to x is being represented by a slanting line for all values of x greater than 1. So let us have the fourth given. Let's say we're trying to look for the value of p of 0. So we need to know where can we find 0 from the given interval of x. So it is obviously x that is less than 2 because 0 is less than 2. So we are going to use p of x is equal to x minus 4. We let x be equal to 0. So p of 0 is now 0 minus 4. P of 0 is negative 4. Okay, so let's have the next. Let's try to look p of 5. So 5 is greater than 2. So we're going to use the first subfunction p of x is equal to 1 over x. We substitute, so p of 5 is equal to 1/5. Okay, so what about p of 10 minus p of negative 2? Okay, so if that is a problem, you can break it down first. Let's start from solving p of 10. So p of 10 is 10 is greater than 2, so we're using the first function. 1 over 10 is the answer for p of 10. However, for p of negative 2, negative 2 is less than 2, so we're using the second subfunction x minus 4. Substitute negative 2 to x, so we have negative 2 minus 4. So p of negative 2 is negative 6. So after having these two values, p of 10 and p of negative 2, we now go back to our problem and substitute. Therefore, we have p of 10 is 1 over 10 minus negative 6. So 1 over 10 minus negative 6 is 1 over 10 plus 6. Cross multiply 10 times 6 is 60 plus 1 is 61. So we have 61 over 10. Now, since piecewise function is a combination of two or more functions, we can also have a function that looks like this. F of x is composed of the following subfunctions. We can also have a logarithm. So we have logarithm of x. Remember that logarithmic function can also be a part of piecewise function. We can have natural exponential function e raised to x, and we can also have 2 raised to x exponential function. And let's try to identify the subdomains. Let's say we can only use f of x that is equal to logarithm of x if the values of x is greater than 0. So we can use e raised to x, f of x that is e raised to x, when the values of x is less than or equal to 0, but greater than, let's say, -1. Now we can use f of x that is equal to 2 raised to x if the values of x is less than or equal to -1. Okay, so as you observe, I am also identifying distinct domains or subdomains of each subfunctions. And let's try to answer what is f of 2. Okay, what is the value of f of -2? And what is f of 0? Okay, let's start from answering f of 2. So the first thing we need to do is to again identify what interval is being satisfied by x that is equal to 2, and that is obviously on the first subfunction, the logarithmic function. So we are now using f of x is equal to logarithm of x. We let x be equal to 2, so we have f of 2 is equal to logarithm of 2. F of 2 therefore is approximately, okay, the exact answer is logarithm of 2, but when you're answering, you can also have an approximation, and that is also accepted. The answer is approximately 0.3. So what about f of -2? -2 is less than -1. As you observe, -2 is less than -1, so we are now using the last function. We are using f of x is equal to 2 raised to x. Okay, so we let x be equal to -2, so f of -2 is now 2 raised to -2. Now the rule of exponential negative integral exponent, so we can have 1 over 2 raised to 2, or simply 1/4. So f of -2 is 1/4. So what about f of 0? 0 is found on the second subfunction, natural exponential function e raised to x. So we are using f of x is equal to e raised to x. We let x be 0, so we have f of 0 is equal to e raised to 0. And any number raised to 0 except 0 itself is simply 1. So f of 0 is 1.